Hello everyone. So this is the second lecture in the Riemannian geometry series. I know the second lecture was supposed to be on the examples of the Riemannian manifold. But you see, tangent space is one of the most crucial topic in the modern geometry. You see, the very first object was the Riemannian metric and it is defined over the tangent space. So I think I should at least make one lecture reviewing the concept of tangent spaces. So that's why I'm making it, and rest assured the video on the Riemannian manifold, examples of Riemannian manifold will come. We will do everything. It will go slow, but we will do everything at great details. So let's get into it right ahead. So the moment someone says the tangent vector, what is the image that comes into one's mind? This is the following image comes into one's mind. What you imagine that you have your space, this is your space, and you imagine the tangent vector as arrows originating from a point like this and going to some other point. Now, there is nothing wrong in this picture. It's just it works fine. It works fine in Euclidean space because in Euclidean space we have been doing all the geometry for our all school days in Euclidean space, and every structure that we require is already there, so that's why we can do it. But you see, right now what we are going to do is we are going to define tangent vectors on a smooth manifold. It doesn't work on a smooth manifold. It doesn't look good on a smooth manifold. Why? Because on a smooth manifold, what structure do we have? A set, a topology, and a smooth atlas. If you are imagining a tangent vector as an arrow, then as an arrow originating from a point and going to another point, then that arrow has a length. But on a smooth manifold, we don't have any notion of length. So we cannot talk about some arrows like these. Okay, so I hope you got the point. So this is why we should get away from this kind of picture. This kind of picture works fine when you have a notion of length on the space. But in general, this is not good enough. So let's get into the abstract thing, the abstract topic of tangent vector and tangent spaces. Now for that, we require an object. What object is that? Let's see that. So let's say we have our manifold M. So M is our manifold. What you can do is you can construct a real vector space with the set. What set? The underlying set is the following. This is the set of the functions going from M to R, manifold to R. And not just any function, these functions must be smooth. So F is smooth. Now this set is denoted by C infinity M. So C infinity represents the smoothness. Okay, but right now this is just a set. For it to be a vector space, what we need? We require two operations, vector addition and scalar multiplication. So let's see what those operations are. So the first one is the vector addition. And it's quite simple. How do we define the vector addition? We define it point-wise addition. So let's say for a point P belongs to M. What we do? We define in the following manner. F plus G at P, this is equals to, you evaluate F at the point P, you evaluate G at the point P, and then add them up. This is how you define the vector addition. Second thing is the scalar multiplication. So this is a real vector space. So you take some scalar, let's say lambda, from R, and you define your scalar multiplication just like above the vector addition. So lambda dot f evaluating at the point P, this is defined to be lambda dot f evaluated at the point P. So with these operations, with these two operations, C infinity M, this set that we have, forms a vector space, forms a vector space. And this is an easy exercise of linear algebra. So please check it. This is a very easy exercise in linear algebra. So please check it that with these two operations, this set forms a vector space. Now, consider this our manifold. So let's draw a diagram because it's going to be very useful. So this is our manifold M, and on this manifold we define a curve. So what curve is? On real line you take some open interval, and open interval to M you define a map that gives you a curve. So this is your curve gamma, and this is a curve passing through a point P, and at this point P we want to find out the tangent vector. Now if it was just our Euclidean space, we could have just let's say this curve is such that gamma 0 is equals to P. If this was just Euclidean space, what you have done is just differentiate the gamma and then evaluate at the parameter value 0, and that would have given you the tangent vector at this point. But the problem now is that we are slowly providing the various structure to our bare set M. Right now we don't have any tool to differentiate, to do the differentiation on the manifold. We don't have that. So what we are going to do? What we do, rather than differentiating on the manifold, we can't do that. We differentiate something else along this curve. As we move along the curve, we differentiate something else. What we differentiate? A function. So we define a function f from M to R. You see why I constructed that vector space of a smooth function from M to R. So now you see from this gamma and f you have another function, this one. This is f of gamma. Now f of gamma is a function from R to R, and we know how to differentiate a function from R to R. And clearly this tells you how the values changes as you move along the curve when you change the parameter value in the domain of the curve gamma. Because how can you find out? If you change the parameter value in the domain of the curve gamma, certainly since all of this is connected, the parameter value in the codomain of this function f is also going to change. Okay, so what we do, we differentiate this along this curve. That means we find the derivative of f of gamma. So it will tell us how this thing is changing here in the codomain of the function f when you change the parameter value in the domain of the gamma, and that will tell you how the things are changing on the curve. So that is how we define. So basically this is giving you a derivative operator. So you see we are going to define something called a directional derivative operator. So let gamma from some open interval to R be smooth curve. So this is our smooth curve such that gamma of 0 is equals to P. And we can do this without loss of any generality. Why? Even if you have a curve that doesn't satisfy this property, you can still rearrange your parameter value or reparameterize the curve such that this condition satisfies. You can always do that. So there is no problem. Another thing, this kind of condition makes the formula simpler. That's it. Okay. So this is our curve. Then we define the directional derivative operator, and this point P is actually coming from the n. Then we define, so let me write in another color, define, because this is the important object, directional derivative operator at the point P along the curve gamma. What is it? We denote it by x gamma P. So this is a map from C infinity M to R. So what it does, it takes the function f, so this is the function f from M to R, and it maps it, you know where, I just explained in the diagram, f composed with gamma, differentiate it, and we need at the point P. So we will have to provide some parameter value. That parameter value is going to come from the domain of the curve gamma. So that will be 0 because we have taken gamma of 0 is equals to P. And since this f of gamma is a function from R to R, so we can do our usual derivative, and then you will evaluate it at the point 0. This entire thing belongs to R. Okay, so this is your directional derivative operator, and in manifold theory or differential geometry, this x gamma p is referred as tangent vector. So here we have a crucial point to keep in mind, that when you had your Euclidean space, in Euclidean space you had two concepts, two individual concepts, one concept of direction and one concept of derivative, and then you combine them and you form directional derivative. That was the story in Euclidean space. But here on manifold, you don't have those individual notions of direction and derivative. These two things always come together. As we go along in the course, we will study something called covariant derivative. Even the covariant derivative is a kind of directional derivative. You will say the covariant derivative of a vector field x in the direction of y. Always, no matter what kind of derivative tool we develop on manifold, it will always going to be a kind of directional derivative. In manifold theory, we do not have individual concept of direction and individual concept of derivative. They come together, and this is how it survives in manifold theory. So this is a crucial point to keep in mind. Okay, let's move right ahead. Now we come to our main thing, which is tangent space. What is the tangent space? So you have your smooth manifold M. Okay, M is your smooth manifold, and you have your point P. Okay, I forgot to tell you one thing. I'm not doing it here, but I'm telling you, and you can look it into any book. You see, you might be thinking, oh, how, what is the evidence, like what is the guarantee that directional derivative operator are indeed going to represent tangent vectors? You see, we can actually construct an isomorphism between the set of directional derivative operator and the geometric tangent vectors. I'm saying geometric tangent vectors which are in your Euclidean space. In Euclidean space, you have all the structure, so their tangent vectors have their length. Okay, so that's why I'm adding the word geometric. You can also, you can simply say vectors in Rn. Okay, so you take the set of directional derivative operator and you take vectors in Rn and you can construct an isomorphism between them. Okay, so that's why that is the kind of evidence, and you can look for this isomorphism in any book, like a book by John M. Lee of manifold theory, book by S. Kumrason of differential geometry. You will easily find the isomorphism there. Okay, I'm not doing it here, but I have told you, you can look for it. There are several interpretation of tangent vector. I'm telling you intuitive one, a good one, and a very useful. Okay, so now comes to the tangent space. So what is it? It's actually the collection. What we do, we collect, we denote it by TPM, TPM, and we collect, this is a set X gamma P, such that gamma is a smooth curve through P, this set. So what we are doing here, what we are doing is, this is our manifold, and on this manifold you have this curve, okay, passing through a point P, but you see, this is your curve passing through this point P, but also on this same curve you can go left to right, you can go right to left, you get those tangent vector of two direction. You can go with a different pace, like you can go twice as fast or thrice as fast, so all that. But other than that, you can also have this curve, you can also have like this curve, you can also have like this curve, all the curve, those are passing through the point P. We collected all of them in this set. Okay, that set is a tangent space. Now, but right now, this is just a set. For a set to be a vector space, you need two operations. This is just a bare set here right now. Okay. Now we are going to define two operations here. First one is obviously, like before, is the addition. How do we define it? Well, we take two curves x gamma p and x delta p. Okay, and this operate on f. How do we define it? We define it x gamma p acting on f, and you add it up with x delta p acting on f. Second is your scalar multiplication. So for, let's say, lambda belongs to R, so this is a real vector space, x gamma p acting on f, this thing. But you see, here we still have a problem. What's the problem? In the first, in this addition, when we add these two things and we get this object, this entire object. Now, of course, we understand that we add two same type of functions. Both of these are the function from C infinity m to R. After adding them up, of course, we are going to get a function which is from C infinity m to R. but this only takes care of the 50% of the definition. We still need to show for this, for this result that we got, for this object that we got, for this to be in the TPM, we still need to show that there exists a curve to which it is a tangent. We still need to show that. Only then we can say for sure that whatever this object is, this is indeed in the TPM and this operation is well defined. And the same thing we need to do for the scalar multiplication. Okay, so let's do that. So let's do that. How do we do it? Well, we go into the chart. So let ux be the chart on M. Be the chart on M and P belongs to U. Of course, this is our point of consideration. Then we need to construct the curve. So first I am doing it for the first one, vector addition. For the second one is quite simple. But for the first one, we just need to understand a little bit. Define the curve. Okay, if I will directly write the expression for the curve, you will be like, where the hell did that thing come from? So let me do a little bit rough work so that you can understand what's going on. Okay, let's draw some diagrams. This is your manifold M and you have your two curves. This is your one curve, okay, and this is your another curve. So let's say this is your x gamma p and this black one is your x delta p. Now I want to find a curve here that passes through the same point, and that is actually the sum of it. But we don't know how to do anything on the manifold, and this is your point P. So what we do, we go into the chart and that chart comes with its chart map. So that chart map will map these curves in Rn, right? Now in Rn, so this is your, let's say, this is your x composed with gamma. This is your x composed with delta. Now in Rn we know how to do anything. Okay, we know how to do it. So what you do, you sum it up here. So you sum it up, x composed with gamma and x composed with delta, and after summing whatever you get, you map it back to the manifold. How will you do that? Well, this is a chart map. So chart map is bijective and hence it is invertible. So you can go back onto the manifold. So you take this entire thing and you map it back to the manifold. Let's see if it is work. So this is our obvious guess. Let's see if it will work or not. Is this the curve that we need? Well, if it is the curve that we need, then it must pass through the point P on the manifold. And how do we get the point P? By putting in the parameter value 0. So let's check at t equals to 0 if it gives the point P or not. So x inverse composed with x of gamma of 0 plus x of delta of 0. Okay, so this will give me x of p. This will also give me x of p. Oh no, we have a problem. This doesn't give us p. What does this give? 2 times x of p. Well, you see, we could have had the p if we had only got just one x of p here. So here where we define this function, if I just subtract one x of p, I will get it, what I require. If we will subtract one x of p, this will cancel out and this x inverse composed with x gives me p. Voila, we got our map. So sigma of t, let's define it, sigma of t x inverse composed with x of gamma of t plus x of delta of t minus x of t. Now first thing, clearly sigma is smooth. Why? Because by construction x of gamma is smooth, x of delta is smooth, x inverse is smooth, and we know the summation, the addition of smooth function is smooth, composition of a smooth function is smooth, and sigma is smooth. So that's okay. And we have already done the calculation that sigma of 0 is equals to p. So this curve indeed passes through the point p. Now only thing we need, now the claim is, what is the claim? Claim is that the tangent vector x sigma p is nothing but this object that we are getting after summing up. That is x gamma p f plus x delta p f. So let's prove that. So let's take our x gamma p, x sigma p, sorry, and it will operate on the function, smooth function f. So just apply the definition. We know the definition. This was the definition. Okay, is just the derivative of the composition of the function with the curve. So this will be f composed with sigma. We take the derivative at the parameter value 0. Now we know what the sigma is. So just put in the sigma here. So let's put that here. This will give us f composed with x inverse, and this is composed with, I hope I will not make any mistake while writing it down. Okay, seems I'm writing everything correct. This is it, and then derivative evaluated at the parameter value 0. Now note here, we have two things here. First, this entire function. This is the function from R to Rn. N is the dimension of the manifold that we have taken. And this is a function f of x inverse. See, f is going from M to R. X inverse, this is going from here to here. So obviously this is the function from Rn to R. So here you have the composition of two function. Okay. So what we can do to find the derivative of this is we can apply multivariable chain rule. Now you see, in real analysis, when we had the function like from R to R, we need not worry about, when we say f dash, we need not worry about anything, and we simply write df over dx, because we didn't have many variables, but we can't say that by derivative we mean d over dx always. It can be anything. You don't know. But now we have multivariable things. So we will have to use a different notation like some index to show the components. So we will use x to the a. The index a only represents the component function. Okay. So by multivariable chain rule, what we get the following. So I differentiate this thing with respect to the eighth component and then evaluate it at the point x of p. Okay. because this is a function from Rn to R here. So here you have the point x of p, not p. And then this other function, you differentiate this thing also. And you take the ath component, xa composed with gamma plus xa composed with delta minus xa of p. Okay, and you take the derivative of this. Now here you see the derivative is a linear function. So since the derivative is linear, I can individually differentiate. So this remains as it is, and then I individually differentiate it and evaluate it at the parameter value 0, and this xa of p is a constant, so its derivative is simply 0. Now you can write it in the following way. How you can write it? You can write it as f composed with x inverse composed with x composed with gamma, derivative of this evaluated at the point 0. This is how you can write it. That's what we have done here, because you see f of x inverse is a function from Rn to R, and x of gamma is simply from R to R. And here what you have is f composed with x inverse, and this composed with x of delta and the derivative of this. You can write this as the following. And one more thing I should mention here, that here these xa, where the index a runs from 1 to n, these are not power, these are just indices. Okay, so these x's are the component functions, because x is a function from Rn to R, the chart map. So obviously it has component functions. So these are component functions of x. Okay, and now look at this. What is this? This is nothing but f composed with gamma plus this is f composed with delta, and this is nothing but by definition x gamma p plus x delta p. That's what this is, and hence we indeed prove that this object belongs to TPM, because we have shown that there exists a curve. Similarly, for second, take here there is no problem. A simple curve will do the trick. What is that simple curve? This is the scalar multiplication. So you don't need to define any complicated curve like this. You just take the gamma and you just multiply the parameter value by lambda. That's it. And then you do the similar kind of calculation. That is, you take your x sigma t, x sigma p evaluated at f by using this definition, and you show that this is indeed equals to lambda dot x gamma p evaluated at f. Okay, so this is a similar proof, so do it on your own. Okay, this is quite similar proof, so you can do it. I hope up to here you have understood everything. Now one more little thing that I want to mention quickly, because otherwise the length of the video would be quite long. So let's have a look at this quickly. This is components of a vector. So let's have a look at that. So what we have our chart ux. This is your chart of a smooth manifold M, and you have your curve, a smooth curve gamma from some open interval to M. This is your curve and it passes through the point P. So gamma of 0 is P and this point P comes from U. We have taken the chart. Okay. So see, note that you have your x gamma P. By definition of the tangent vector, what is this? This is f composed with gamma. Take the derivative of it. Evaluate it at the parameter value 0. Now, just for fun, you have your chart. So I invoke the chart map here. How do I invoke the chart map here? Well, chart map is invertible, so I can invoke it like this. Right? There is no problem here. Now again you apply your multivariable chain rule, and what you do? Let's say I have taken the ith component here, xi composed with gamma. You take the derivative of that, evaluate it, and then this outer function. This is the inner function x of gamma, and the outer function is f of x inverse. So you take the ith component of that, del I f of x inverse, like this, and this is evaluated at the point x of p. Okay, now del I, this just tells you which entry to drive. This del I that you have, this tells you that you need to differentiate the ith entry. Now we have a notation. This is a very important thing. Even the book mention it, but sometimes we don't pay attention to it. So I'm writing it, and pay attention to it. Del f over del xi. You have seen this notation. So this is the notation for this thing. Del I f of x inverse. This is the notation for this thing. And similarly, you have this notation. You can write it, but mostly I wanted to talk about this notation, del f over del xi. See, when you look at it, since you have been doing the geometry on Euclidean space, you have been doing Euclidean geometry, the moment you look at this notation, you think, oh, this is the partial derivative. But the thing is, when you are working on a general manifold, this is just a notation. On a general manifold, it is just a notation. It has nothing to do with the partial derivative. Even though, if you take this definition of this, you will see it satisfies all the properties of the partial derivative, but it has nothing to do with it. Even the books mention it very clearly. They write that when you take your manifold to be Rn with standard coordinates, then this del over del xi type thing works as partial derivative operator. Okay, so this is one thing that is what I wanted to mention. My main motive was to review the concept of tangent vectors that I have reviewed, although they are 2, 3, 4 more things that should be done, but I think now you can go and look at those things on your own. The first thing that I haven't done, and you should have a look at it, that thing is, I have already proved that TPM is indeed a vector space. I have defined these two operations and I have shown that they are well defined. So of course TPM is a vector space. But one thing that I have not done, that if you have a manifold M and the dimension of M is n, then dimension of TPM is also n. So please check it from the book. When I will start If I will start making someday the series on smooth manifold, then I will prove this theorem also. But you should at least go on, because right now my goal is to make the playlist entire series on Riemannian geometry, and this comes in the prerequisite. But still, I wanted, since it is the concept of tangent space and tangent vector is quite important, so I just wanted to review the definition of it. So that's what I have done. Please do it. Have a look at this proof, or for now, proof is for this, like for the clarity, okay, that this is actually true, okay. Other than that, right now you can keep it in mind that the dimension of the TPM is same as the dimension of the manifold that you have. And these things that you are having, del over del xi, these are the basis vectors. These are actually the basis vector, these del over del xi, del over del xi. These are the basis vectors of the vector space TPM. And you remember we used that in the first video of Riemannian manifold. In Riemannian metric, your Gij's were nothing but G of del over del xi and del over del xj. So that's what these things are. Okay. So all of this. So this is enough for the today's lecture, and I hope you enjoyed it. Thank you for watching.